Hey guys, welcome to your very first flipped lesson on patterns and inductive reasoning. Geometry, like much of math and science, is developed when people begin to recognize and describe patterns that they see around them. Let's take a look at our first pattern of the day. Notice that in our very first figure, there are 3 blocks. In our second figure, there are a total of 6 blocks. And in the third figure, there's a total of 9 blocks. Based on this pattern, one might assume that to get to figure 4, we're going to add an additional 3 blocks. This seems like a good guess, and I think we were right. Notice that this fourth figure has a total of 12 blocks, just like we predicted. We just used inductive reasoning to come to this conclusion. Inductive reasoning is the process of looking for patterns and making conjectures based on that pattern. This is a simple 3-step process that we're going to utilize throughout the entire semester. Step 1 is looking for a pattern. Step 2 is making a conjecture. And step 3 is verifying that conjecture. Let's also formally define what a conjecture is. A conjecture is an unproven statement that is based on observations. So let's go ahead and continue to use our inductive reasoning process to answer a few more questions. Here's another visual pattern for us to look at. Notice that figure 1 has 1 block, figure 2 has 4 blocks, and figure 3 has 7 blocks. It looks like we're adding 3 additional blocks every single time. Specifically 1 on the top, 1 on the back, and 1 on the right-hand side. Notice that we have picked up on the correct pattern by looking at figure 4. We can also look at number patterns as opposed to visual patterns. We have to identify how are we getting from the number 1 to the number 4. Well, we could be adding 3, but we could also be multiplying by 4. If we take a look at the next step, I think that multiplying by 4 seems most appropriate. Based on this pattern, one would conclude that to get to the very next piece, we would have to multiply by 4 again, giving us 256. Let's look at one more number pattern. To get from -5 to -2, it looks like we're adding 3. To get from -2 to 4, it looks like we're adding 6. And to get from 4 to 13, it looks like we're adding 9. Based on this pattern, one might assume that to get to the next term, we're now going to have to add 12, giving us 25. When making a conjecture, we have to examine several examples to help us identify a pattern. Take a look at the given conjecture. The sum of the first n odd positive integers is blank. Now, in order to fill in this blank, we're going to have to look at some examples to help us pick up a pattern. Let's first look at when n is equal to 1. That would be the sum of the first odd positive integer, which the sum of just 1 and nothing is 1. If n equals 2, the sum of the first 2 odd positive integers is going to be equal to 4. If n equals 3, the sum of the first 3 odd positive integers is equal to 9. If n equals 4, the sum of the first 4 odd positive integers is equal to 16. Now, after looking at these 4 examples, I'm starting to notice a little bit of a pattern that's occurring. Notice that these are all perfect squares. So let's represent them as perfect squares. This would be represented as 1 to the power of 2. This would be represented as 2 to the power of 2. This is represented as 3 to the power of 2. And this is represented as 4 to the power of 2. With this new representation, hopefully you're seeing a relationship from when n is equal to 1, our value is equal to n squared. When n is equal to 2, our value is equal to n squared. If n is equal to 3, our final value is equal to n squared. Based on this pattern, I feel comfortable filling in the conjecture as the sum of the first n odd positive integers is n raised to the power of 2. Now, we haven't formally proven that this conjecture is true, but based on a pattern, we feel comfortable making this conjecture. Now let's talk about how we can disprove conjectures. To disprove a conjecture, we need to have a counterexample. A counterexample is an example that shows a conjecture is false. So let's see if we can read this conjecture and prove it false. For all real numbers x, the expression x squared is greater than or equal to x. Well, let's look at an example. If x is equal to 2, then x squared is equal to 4. Well, 4 is greater than 2, so this case actually checks out. Well, this is saying all real numbers. That means negative, positive, whole numbers, decimals, fractions. So I could think of a counterexample that's a fraction. If I let x equal 1/2, then x squared is equal to 1/4. Notice that 1/4 is not greater than 1/2. Therefore, x equals 1/2 is a counterexample for this conjecture. Now let's talk about unproven conjectures. Here we have a picture of German mathematician Christian Goldbach. He's famous for a conjecture he made that states every even number greater than 2 can be written as the sum of 2 primes. Well, let's quickly recall that prime numbers are numbers greater than 1 that are only divisible by 1 in itself. So, 2 is a prime number, 3 is a prime number, 5 is a prime number, 7, 11, and we could continue this list further. Let's illustrate what his conjecture states. Every even number greater than 2, so let's start with the even number 4. Can we represent 4 as the sum of 2 primes? I think we can. 2 plus 2 equals 4. Let's look at the next even number. Can we represent 6 as the sum of 2 prime numbers? I'm seeing 3 plus 3. Let's take a look at 8. Can I represent 8 as the sum of 2 prime numbers? I'm seeing 5 plus 3. We could continue looking at different cases, showing that Goldbach's conjecture follows. While this has never been formally proven for every single even number greater than 2, it has been proven up to the number 4 times 10 to the 14th. So they have proven a lot of cases. We just haven't proven this case to be true in general. As a quick reminder, this is written in scientific notation. In order to figure out what this number is, we're going to take the number 4 and we're going to move the decimal point 14 places to the right. This shows that we have proven this conjecture true for a lot of cases, but just not every case yet. The major takeaway from that conversation is to remember that just because you prove something is true for several specific cases does not prove that it's true for every case in general. We will learn how to prove conjectures later in this course, but just not today. In 2005, the first 6 full moons occurred on January 25th, February 24th, March 25th, April 24th, May 23rd, and June 22nd. If you take a look at a calendar and count the days out, hopefully you would notice that a full moon was occurring every 29 to 30 days. Based on this observation, one might conjecture that a full moon occurs every 29.5 days. And a simple internet search actually shows that this is true. The moon does revolve around the earth once approximately every 29.5 days. So, the major takeaways for this lesson is to know what a conjecture is, what inductive reasoning is, and what a counterexample is. And just keep in mind, we haven't learned how to formally prove conjectures yet, but we did learn how to disprove them with counterexamples. Thanks for joining today.